Module 5 time, and the first thing you'll notice is that Module 5 contains two chapters. We're studying chapters 5 and 6. We're picking up the pace a little bit, so you'll have to read a little bit quicker this week. One thing I want you to notice is that Module 5 has two main themes. The first theme is that astronomy is all about light. Okay, terrific. What I mean by that is that astronomers, they study stars. Stars are just little pinpricks of light, insignificant pinpricks of light, in the sense that they're so small and so faint that we don't see them during the daytime. We know they're out there in our daytime sky, but they're so insignificant that our sun just overwhelms them. So there's not a whole lot of information reaching Earth from these little pinpricks of light that are stars that are way, way far away. And astronomy is different than other sciences in the sense that in chemistry, if you want to learn what happens when an acid and a base mix together, you go down to the lab and you do it. You grab an acid, you grab a base, you mix them together, you take some measurements. We can't do that in astronomy. We'll never travel to those stars. We'll never be able to sample them directly. We have to do it remotely with a tiny amount of information, remember? And so the job of the astronomer is to harvest that light using equipment we call telescopes. That's the subject of chapter 5. And from that small amount of data, we can extract so much information about those stars. Even though we'll never travel to them and sample them directly, we can learn a lot about them using basic physics. That's the first main theme. The second main theme of this module is that the human eye stinks. There may be people who will tell you, oh, how wonderful the human eye is. I'm here to tell you that they're wrong. They don't know biology, they don't know physiology, and they don't know physics. How can I prove that? Behold, this little piece of paper that has an X and a dot on it. What I can do is I can hold that piece of paper up, look at it, close one eye, I'll close my right eye, and I'm going to bring this slip of paper right about here. I'm going to stare at that black dot. When I stare at the black dot with my left eye, something happens right about at this spot. The X disappears on me. I have placed my paper at the proper distance so the X is in what I call my blind spot. It turns out that in our eye, the retina, which is where all of our rods and cones, all of our photoreceptors are, there's a place on the retina where the optic nerve connects to the retina, and there are no photoreceptors there. So there's no, where that information from the X is hitting my eye, my left eye, there are no rods or cones at that spot. I'm not getting any light information. So what does the eye do? The eye fills in, so now what I see is essentially just white paper. Even though it's not getting any information there, the brain fills in that spot, so I don't see nothing there. I just see white. That's because it looks at the context and it fills in that empty space. Now, when I've got both eyes open, the brain, what the left eye doesn't see, the right eye does see, and therefore it fills it in. So the brain accommodates, but it's not a very good design. It's lousy. But don't feel bad. Don't let it affect your self-esteem. You're still good people. Who else suffers from the same problem? Just ask your cat or your dog. They have the same problem. In fact, all vertebrates have the same problem because the vertebrate eye evolved the same way. If we could go back and change it, perhaps a human engineer would do so, but we can't. Who's got better vision than you? Cephalopods. Invertebrates like squid or octopi, they don't have the blind spot problem because their eye evolved separately. But beyond that, just beyond physiology, there's another problem with the human eye, is that it is very limited. It only sees the visible spectrum. And it turns out there's so much more out there called the electromagnetic spectrum. And that's what we'll be studying in chapter 6. There's so much more out there, and we can't see it directly with our human eyes. However, the human brain has invented devices that allow us to see these other types of light that make up the electromagnetic spectrum. Okay, so light travels at the speed of light. That should be no huge surprise, but one thing that is important for you to understand is that when we talk about the speed of light, it's usually written as c, and it was actually made famous by Einstein in his famous equation, E equals mc squared. And we're going to actually talk later on, when we get into chapter 7, about that equation there. But the c in that equation is the speed of light. The speed of light is not infinitely fast. Light does travel at a very, very fast rate, but it is not infinitely fast. It travels at a speed of 300,000 kilometers per second, as you notice here. That's another way of putting that is 300 million meters per second, or in more American units, 186,000 miles per second. Which means, if you recall, when we did that little Eric Idle Galaxy song, we talked about how far around the Earth is. The Earth is 25,000 miles around, which means that that light can zip around the entire Earth about 7 times in 1 second. That's how fast light travels. So light does travel extremely fast, but it does not travel infinitely fast. It does take light time to travel from one location to another, which is why the sun, we talk about it being 1 AU away. We talk about it being 93 million miles away. Another way of referring to the sun is that it is 8.3 light minutes away, in the sense that the light that we see right now from the sun actually did not leave the sun right now. It left the sun 8.3 minutes ago. So we are not seeing the sun as it is right now. We're seeing the sun as it was 8.3 minutes ago. And when we talk about stars, such as Proxima Centauri, the next nearest star, it's 4.3 light years away, which means that it is so far away that the light that is arriving from Proxima Centauri right now actually left 4.3 years ago. That's how far away it is. You saw on the last slide that there is a relationship between the wavelength and the frequency of a wave. And that relationship is that when you multiply the wavelength times the frequency, you get the speed of light. Anytime when you're talking about light waves, if you multiply the wavelength by the frequency, you get the speed of light, which is c. And so this little simulation then has it gives you a chance to change the wavelength of your particular type of light. So in this case, we're going to start out with a wave that has a wavelength of 1 times 10 to the 0 meters. That's a fancy way of just saying it's a wavelength of 1 meter long. Which 1 meter, that's a pretty long wave. If you think about what a meter is about 3 feet, right? About a yardstick. So that wave then goes through 1 full cycle in 1 meter. That's a pretty big wave. And it has a certain frequency. It turns out the frequency is 300 million hertz, because when you multiply the frequency times the wavelength, you will get 3 times 10 to the 8th, which is the speed of light. Now notice another thing is that we can talk about waves as having energy. And to find the energy of a wave, you just multiply the frequency of the wave times a constant we call h. It's Planck's constant. Don't worry about the constant. The important thing is for you to understand is that as the frequency goes up, the energy goes up. So higher frequency light has a higher amount of energy. So let me now play around with the slider a little bit. Notice also there's a little black body color. So a wave of this type, if we had a source that was producing this kind of wave, it would look reddish to us. Now let me go ahead and change, and a couple other things. The size of the wave is really large. What you would collect that wave with would be a radio telescope, in this case. This is a radio wave, it turns out, because we're on this end of the spectrum. Notice how the wavelengths, they increase from left to right on this diagram. Frequency then increases from right to left. They're inversely proportional. As the wavelength of a wave goes up, its frequency goes down. So let me go ahead and slide. Let's slide to the left. So notice what's happening. My wavelength is getting smaller and smaller, and the frequency is getting larger and larger. But if I multiply the wavelength times the frequency, I'm still going to get the same value. So notice what's happened now. I've gotten into the part of the spectrum where now I'll be using a microwave to receive this kind of wave. I'm getting even smaller wavelengths. Now I'm talking about infrared. And even farther to the left here, now I'm talking about visible type of light. Again, notice how the wavelengths are getting smaller and smaller, the frequencies are getting larger and larger. Notice also what's happening. Notice the energy is getting larger and larger and larger. Why is that? Because my frequency is getting larger and larger. Now I'm in the ultraviolet. Again, these are very small waves. I would have to use an ultraviolet telescope to receive them. Even smaller, now I'm talking about X-rays. smaller wavelengths, higher frequencies. And getting even further extreme to the left here, I would use a gamma ray observatory to receive these type of waves because they're gamma rays. Really small wavelengths, very high frequencies, extremely energetic. Okay, so now that we know that light is more than meets the eye, what meets the eye, we only see the visible spectrum, which is just a sliver of all that is out there. So the human eye is relatively limited because it can only process the visible wavelengths. But Geordi LaForge from Star Trek's Next Generation, blind since birth, was fitted with a thing called the visor, which allowed him to see wavelengths other than just the visible. So I did a little bit of research on Geordi. Geordi could actually see radio waves and microwaves. He could even see into the X-ray, at least according to the information I was able to dig up on Geordi. So he could see way, way more than just the narrow visible spectrum, which may seem great, I guess, but just think about if you were Geordi LaForge, what you would be seeing. You would actually be seeing people's like cell phone conversations and stuff. So that would be, not just hearing it, seeing it. That would be horribly confusing. You'd be bombarded with so much information. You would have to actually be relatively selective in the information that you would be focusing on. Even if you were Geordi LaForge, it would do you precious little good here at the surface of the Earth because the Earth has an atmosphere. And what this graph shows you is the transparency of the atmosphere with respect to wavelength. So it turns out that even if you were Geordi, you wouldn't, and you had the capability of seeing all these different wavelengths of light, you wouldn't see them all if you were at the surface of the Earth. Why is that? Because the Earth is only transparent to a couple of windows. One window is right in here in the visible wavelengths, and then there's another window here in the radio wavelengths. And therefore, and that is part of the reason why the human eye evolved the way it does. The human eye only sees visible light. Why is that? Because only visible light reaches the surface of the Earth, and of course, and radio light as well, radio waves as well. But this is part of the reason why the eye has evolved the way it did, because that's the only information that's gotten through the atmosphere. If you look at the gamma rays and X-rays, this part of the spectrum down here, all that stuff gets blocked out by the atmosphere. Even into the ultraviolet gets blocked out. Most of the infrared blocked out. Most of the radio wavelengths get blocked out as well. But there are only a couple of windows where that information can actually reach the surface of the Earth. Okay, so this slide is going to get you familiar with some of the terminology used in a telescope. So a telescope, its goal is to harvest light. And as it turns out, the larger the telescope, the more light you can harvest. We're going to talk about that in a few slides. But there's two main types of telescopes, refractors and reflectors. Refractors use lenses. Use a piece of clear glass that is shaped to bend light and essentially focus it. Reflectors use mirrors. And here's some terminology of what's called the focal plane, where the light, the distance between the center of the lens and where that lens focuses the light, which is what we call the image, that distance is called the focal length. And reflectors, refractors, they both do the same thing. Essentially, they focus light. Almost all modern telescopes are reflectors, and there's several reasons for that. First of all, with a lens, you have to support it because the light has to pass through it. You can't block the lens. You can only support it on the outsides. And glass gets really heavy, especially when you get large lenses. And that means that the telescope gets really heavy, and to engineer it to hold the lens just on the outside gets to be quite a feat. So it's a lot easier to make reflectors, because reflectors, you can support the entire backside of the mirror. So almost all modern telescopes are reflecting telescopes, not refracting telescopes. Remember, one of the main themes of this module is that astronomy is all about light. That's what astronomers do. They collect light. And So in astronomy, size does matter in the sense that when you're trying to collect light, it's just like when you're trying to collect rain. If you want to collect a lot of rain, you put out a big old barrel. Same thing with light. Telescopes are just essentially buckets for light. And you want to collect more light, you get a bigger telescope. You get a bigger, what's called primary objective. Okay, that could either be a lens or a mirror. If it's a refracting telescope, you want to have it's going to be a large lens. If it's a reflecting telescope, it's going to be a large mirror. But the primary objective has got to be large. And the larger it is, the more light you can gather. In fact, by double, it goes by the area of your lens. So area is given by pi r squared, or so area, which the area of a circle is pi r squared, or in this case, it's the radius is written as diameter divided by 2. But notice when this doubles, when the diameter doubles, notice the impact that would have on the area. By doubling the diameter, you actually quadruple the area. If you triple the diameter, you nine-tuple the area. So that's because of the squared factor in the equation. So it really does make a difference. When you have a 4-inch telescope compared to an 8-inch telescope, the 8-inch telescope is twice the size, but its light gathering capability is actually 4 times as great. You quadruple your light gathering power by doubling the size of your primary objective. Okay, so a large telescope, first of all, allows you to gather more light. It also increases what's called the resolving power of the telescope. And all that resolving power is how close 2 objects can be and still be able to see them as 2 separate objects. So for example, 2 stars out in space. And this is common. There are certain stars out there, such as there's Mizar and Alcor in the Big Dipper, that to the naked eye are tough to resolve. They actually are 2 separate stars, but it's tough to see that with just the naked eye. You put a telescope on them, and now, remember your eye is just a light gathering. Your eye is like a telescope, except for your eye has this little pupil. That's the size of your primary objective in your eye. When you use a telescope, you're essentially creating a much larger eye, a much larger pupil. And so therefore, by looking at looking through a telescope at, say, a double star like Mizar and Alcor, you are increasing your resolving power. You're making the minimum separation between 2 objects much smaller. And that's, again, by this little equation. This funny-looking Greek letter, alpha, that's, again, the angular separation between 2 objects. And that will decrease as you increase your diameter, the diameter of your primary objective. So again, the larger your telescope, when this goes up, this goes down. The closer 2 objects can be, and you can still resolve them as 2 separate objects with that telescope. Okay, then we get to the third power, which is actually the least important power of a telescope, but it's the biggest selling point for a lot of telescopes. Around Christmas time, you'll start to see telescopes in the big box stores, and on the side of it, it'll say 50 times magnifying power, or 100 times magnifying power. And that sounds really impressive, but it's actually the least important part of the least important power of a telescope. If you're going to invest in it, because it turns out that you can make this M, the magnifying power, really large by just making a really small eyepiece focal length. So you can wind up with 50 times magnification or 100 times magnification by just making this eyepiece focal length really small. But it turns out that really small telescopes that don't have a large primary objective are not going to gather very much light. They're not going to have a very good resolving power. And so by creating a large magnification with a very small eyepiece focal length, all you're really doing is like turning up the volume. It's like if you've got a staticky radio station. When you turn up the volume, you're amplifying the signal, yes, but you're also amplifying the noise. It's still going to sound lousy. And so therefore, magnifying power is really not that much of a selling point. If you're going to invest in a telescope, the best thing to do is buy a big scope. That's going to improve the quality of the signal and then you can amplify it as much as you want. Okay, so now that you're familiar with some of the different powers of a telescope, light gathering power, resolving power, magnifying power, let's see them in action using this telescope simulator. So notice we're looking at the moon, and we're using an 8-inch telescope with an eyepiece that's 40 millimeters focal length, and we're looking at the moon. And so there's several different things we see here. The light gathering power of this telescope is 840 times that of the human eye. So this is a big scope, and it can gather a lot more light than the human eye can. Its resolving power, the resolution here, is 0.5 arc seconds. And the magnification is 35. Notice to get the magnification, we can use the focal length of the primary objective, which this is a big telescope, and therefore it's got a long focal length for the primary lens here. This is a refractor. And then we divide that by the focal length of the eyepiece, which is 40, and we get 35 as the magnifying power. Now let's change. Let me change the aperture, meaning the size of the telescope. Notice what happens when I go from an 8-inch to a 6-inch, or even down to a 4-inch. Notice anything in the image? You should notice one thing is that, well, first of all, the image gets smaller. And that's because, notice, the magnifying power has decreased. But also, the image becomes dimmer, doesn't it? Because I'm gathering less light. Okay? Now, what else could we do? We could, what would happen if I changed my eyepiece? Going back to my 8-inch telescope, let me change my eyepiece to a 20 millimeter or a 10 millimeter. Notice what happens here. Again, I'm decreasing my eyepiece focal length, and therefore I'm increasing the magnification. So I'm magnifying that image more by changing my eyepieces. But again, that's kind of limiting. You wouldn't necessarily want to go to a, let's say we got let's see, my 4-inch telescope. Using the large eyepiece, I get a pretty nice image. When I switch to a 10, the image kind of looks crappy. And that's because I'm amplifying both the signal and the noise here. But again, this just kind of gives you an idea as to the different powers of telescopes. Light gathering power has everything to do with the size of the telescope. The larger the telescope, notice my 8-inch telescope has a light gathering power of 840 times that of the human eye. When I use a 4-inch telescope, just half the size of it, notice that it's only 1/4 the light gathering power, only 210 times the light gathering power of the human eye. We also get the resolving power and the magnifying power of these various telescopes. Okay, so we've already talked about the fact that Earth-based telescopes are rather limited. They can only look at stuff that's in the visible or in the radio. But let's say you could put some telescopes in space on a satellite. What would you look for? Well, it turns out that if you're looking at something that's very, very energetic, like a star that has exploded, that's called a supernova, an exploding star produces a huge amount of energy at extremely high temperatures. So that type of an event produces a lot in the way of gamma rays. It produces all kinds of radiation, but for the most part, it produces your most energetic type of light, which is gamma rays, and therefore you would use a gamma ray observatory. If you're looking at like the active center of a galaxy, which is also quite energetic, you're going to be looking at something that's producing a lot of X-rays, and therefore you'd use an X-ray telescope. If you're looking at just kind of normal stars, they tend to peak in the visible end of the spectrum, and therefore you would use something like the Hubble Space Telescope. If you're looking at clouds of gas and dust out in space, relatively cool objects, they're going to be producing mostly infrared or even radio wavelengths, and therefore you might use an infrared telescope for those type of objects. The infrared is a relatively interesting band of wavelengths because, as mentioned, the atmosphere screens out a lot of infrared. And so the obvious option is to put a satellite in space to observe infrared. The problem with space-based telescopes is that they're really expensive, not only to build them, to launch them, to maintain them, but they can't really be changed very much. Once you've put it up there, it's tough to alter the mission of the telescope. So another option is to use high-altitude aircraft. essentially fly high into the atmosphere, so you're putting most of the atmosphere below you. Stick a telescope out the side of the aircraft and observe that way. It's much cheaper. You can change the telescope a lot easier by doing it in an aircraft as opposed to satellite. So that's one thing that's an active area of astronomy is infrared using aircraft-based telescopes rather than satellite telescopes. Okay, so we already talked about resolving power, and in fact, we talked about it with respect to this equation. And you don't really have to understand, you don't have to memorize the equation, certainly. But one thing that you do have to understand is that one thing we already dealt with was the fact that when you increase the diameter of your telescope, when you increase the diameter of your primary objective, this D value, when that goes up, notice what happens to the minimum angular separation between two objects that can be resolved as two different objects. That goes down, right? But notice there's another factor involved. These are not all constants. This can also change. This is the wavelength at which you are observing. So for visible telescopes, the wavelength of visible light is relatively small. And so when we're looking at visible telescopes, increasing the D makes the alpha get smaller. But let's think about other types of light other than just visible light. What if we're talking about radio telescopes? Well, radio waves are really, really big. And therefore, since the wavelength is really large, the angular separation between two objects is going to be pretty large. Or it has to be pretty large in order to see them as two distinct objects. Since that lambda gets really large, you also have to make the D really, really, really large. And sometimes it's impractical to make a telescope that large. What you can do, what astronomers have figured out, is that you can actually combine several signals from different telescopes. You don't have to build one huge telescope. What you can do is build several smaller telescopes relatively close to each other and then combine those signals. And essentially what that does is it creates a simulation of a telescope that is indeed that large. So that's a process called interferometry, combining the signals from several smaller telescopes to essentially make one large virtual telescope. Okay, so all of Chapter 5 we talked about how telescopes handle light. Chapter 6 talks about the nature of light. And I'm not going to go through the entire structure of the atom stuff. That's in your book. It's also a large part of the hydrogen atom lab activity you're doing this module. So I'm going to assume that you understand the basic structure of the atom. But what's interesting is that due to the structure of the atom, all atoms are laid out a little bit differently. So something like hydrogen, as we see here, has a nucleus, as does helium and boron, and they have different numbers of protons, different numbers of positive charges, and that affects the structure then of what are called the electron energy levels. Hydrogen only has one proton, has one single positive charge in its nucleus, and therefore an electron is going to be bound to the nucleus. There's going to be an attraction because an electron has a negative charge, right? So there's going to be a certain amount of attraction, but since there's only one electron and one proton, they're not that attracted, and therefore your first energy level is actually pretty far away from the nucleus. It's out here. Whereas notice with helium, the first energy level is closer because there's two positive charges. There's a little more pull there, right? And with boron, you notice that the first energy level is even closer. That's because boron has more protons, and therefore there's more of a pull there. So notice that the way the energy levels are laid out is different for different elements, and that's really important because that provides essentially a fingerprint. Because of these different energy level structures, this creates different types of essentially fingerprints and allows you to understand the elemental makeup of stars. Okay, so now here's where that equation that is very important. Again, not actually memorizing the equation, but understanding that light of different frequencies has different energies. And so a particular type of, whether it's, let's say, a radio wave has a long wavelength, low frequency, low energy. An infrared light or I'm sorry, ultraviolet light has a shorter wavelength, higher frequency, higher energy. So different types of light have different amounts of energy, and those different amounts of energy are crucial because now parcels of light are what we call photons. And we can see three different photons here. We see a kind of a long loping wave here. That's going to be a low frequency, low energy type of light. Here's a slightly shorter wavelength, higher frequency, higher energy light. And here is the most energetic of these three photons. It's got a shorter wavelength, higher frequency, higher energy. Notice that these photons are hitting electrons in this atom and giving those electrons energy. And again, the photons have to have the right amount of energy. So this particular photon here that the red arrow is pointed at has just the right amount of energy that it allows an electron to absorb it and gain enough energy to go from the first energy level all the way up to, which is called the ground state, up to the third energy level, or what's called the second excited state. Again, by absorbing that right amount of energy. Photon is absorbed and the electron gets kicked up into a higher energy level, which means it's called, the word there is excitation. Okay, if you've already done the hydrogen, if you've done the lab activity for this module, it's entitled Hydrogen Atom, or Hydrogen Energy Levels, I think is the actual title of the lab. But this is the simulator you wind up using. So I'm not going to go into a great amount of detail because I've already got some tutorial videos in the lab itself, which help step you through the simulator. But let me just show you that we've got a hydrogen atom, it's got a proton, it's got an electron. And what this simulator allows you to do is to fire photons of different amounts of energy. Notice that it shows the, right now I'm going to fire a photon. Let's see, it's going to be a 271 nanometer photon, and it shows the corresponding frequency of that photon and the amount of energy of that photon. So if I fire that particular photon, there it is, and notice it does nothing because it's not the right amount of energy. That is not the right amount of energy to give to this electron to allow it to jump to higher energy levels. So notice that had absolutely no effect. Now let me shoot notice we've got these different little buttons down here. These stand for the different types of photons that you can fire at your electron. And I encourage you to, and the L stands for Lyman, the P stands for Passion, and the H's here stand for Balmer. And again, this is something you can read up in the book. But let me go ahead and shoot a Lyman alpha. Notice that that was absorbed. It kicked the electron from its ground state up to its first excited state. That was the Lyman alpha. Now notice it didn't stay excited for very long. It turns out that even when a photon is absorbed by an atom, typically de-excitation happens almost immediately. So the atom absorbs a photon, and then it emits a photon almost immediately. So most atoms don't stay excited very long. They usually get excited, then they emit almost immediately. But that's the basic operation of this hydrogen atom simulator. Okay, so several things I want you to understand on this slide. First of all, stars produce light. That should be no surprise. That's part of the definition of a star, is that it's a self-luminous object in space. So it produces light. Turns out, though, that not all stars produce the same amount of light or the same type of light. And so one of the important things for you to understand is that we're looking at 3 different stars here, and these are different temperature stars. Notice that it's listed as 7,000 K, 6,000 K, 5,000 K. K stands for Kelvin. Those are different temperatures. So again, the higher number, the higher the temperature. These are, so cool star at the bottom, medium temperature star, and then a hot star. Well, yeah, relatively. So notice the difference now in the shapes. The 7,000 Kelvin star is much taller, right? What we're seeing is the light intensity on the y-axis, and we're seeing wavelength on the x-axis. And so one thing that's important to understand with all these graphs is that a star does not produce just one particular color of light. It actually produces a large number. It produces all the colors of light, as well as stuff outside of the visible spectrum. Turns out that all these stars are producing some ultraviolet. All these stars are producing some infrared in addition to all the visible light that they're producing. But notice that they don't produce equal amounts of all these different types of light. So our hot star, our 7,000 K star, produces a lot of ultraviolet, produces a lot of visible, and produces a lot of infrared, compared to, let's say, the 5,000 Kelvin star. And we see that by just the shape of the curve. This one, much taller, much more greater intensity at all wavelengths compared to the 5,000 Kelvin star, right? So that's one thing for you to appreciate, is the fact that a hotter star is going to produce essentially more intense light at all wavelengths. Notice another thing, though. Notice where the peak occurs. That's what's called the lambda max. It's where, in this light intensity curve, where does the peak occur? Notice for the hot star, the 7,000 Kelvin star, it occurs over in the purples, whereas for the cool star, the 5,000 Kelvin star, the peak occurs kind of in the orange area. So that's something called the Wien's displacement law. The hotter the star, the farther to the left on these type of curves, you're going to find the peak. Okay, so let me give you a quick simulation or demonstration of these different blackbody curves. So notice again, we've got a graph here that's going to show the intensity of the light versus the wavelength. And what we have here is we've got a nail that's connected between two electrodes. So we're actually going to run current through a nail and make the nail get really, really hot to the point where it's going to glow. So I'm going to hit the start button. We'll see what happens. So notice it's heating up. Notice how the temperature is climbing, 1,000 Kelvin, 1,100 Kelvin, etc. And notice what happens here on our curve. This nail is now glowing hot. It's producing a lot of visible light. Notice it's also producing infrared light as well, until eventually, boom, it heats up so much that the nail actually melts. And notice what happens now. The nail starts to cool down. It's producing less and less visible light, until eventually we don't see it anymore. Not that it's not producing any light, it's actually producing some infrared, but we're not seeing any visible light there. Okay, so this simulation allows me to play around with different types of stars. So right now we've got a 6,000 Kelvin star, and we have a graph that shows essentially the intensity of the light that it's producing versus wavelength. So again, the star does not just produce one type of light. It produces a huge range of light. Everything, it's producing visible light, it's producing infrared, it's producing ultraviolet, etc. And we see that it does have a peak. It tends to peak at this temperature. We've got a star that's peaking essentially in, kind of the bluish area. Now, what if we, I'm going to go ahead and I'm going to save that one. And now let's add another graph that's going to show, let's choose a cooler star. So let me go down to a 5,000 Kelvin star. Oops. So 5,000 Kelvin star. Notice that this star, auto scale. So remember that the red line now is our 6,000 Kelvin star. Notice that our green line is now our 5,000 Kelvin star. And what do you notice? Well, first of all, the curve is not as high, right? It's producing less energy. It's a cooler star. It's producing less energy. And notice another thing. Where it peaks, again, it's producing infrared, ultraviolet, visible, but it peaks a little bit farther to the right, meaning that it's got its peak type of energy is, again, visible light, but this is more like a yellowish type of light, orangish perhaps. It's a longer wavelength type of light where the peak occurs. Okay, so now we're actually going to, what we've seen in these simulations in the last couple of slides, we're actually going to put into a couple of laws. First of all, we've seen that the hotter the star is, the more energy it's kicking out. And the equation is actually what's called the Stefan-Boltzmann law. So the luminosity, or the amount of energy that a star kicks out, depends upon, as we've seen, the temperature. There's also a constant here that's called the Stefan-Boltzmann constant. We don't care about that. And then there's also area. We're going to talk more about the area in future chapters. But one thing we can clearly see is that as the temperature goes up, the energy that the star produces goes up. We also see that as the temperature increases, the wavelength at which the maximum of its curve occurs is decreasing. So as we saw, as the temperature goes up, as that goes up, notice the way this equation is. We got some sort of a number here, 3 million nanometers, divided by the temperature. Because the temperature is in the denominator, as the denominator goes up, this overall fraction goes down. So that's why the peak tends to occur at smaller and smaller wavelengths, the hotter the star is. Okay, I'm going to try to give you an example of a continuous spectrum. What I've got back here is I've got a light bulb. Of course, what does a light bulb do? What happens in a light bulb is you run electric current through a tungsten filament, just a piece of metal, it's solid, and it heats up. In fact, it heats up so much that it glows. It produces visible light. And we see it as white light, but in reality, it's actually all the different colors of the visible spectrum. Now I'm going to try to give you a look at that entire spectrum using this piece of equipment. And it's really pretty simple, just a little tube. It's got a little slit on this end. That's going to allow the light in, but only a small amount of light. So we're going to get a little slit of light. And on the other end, I have what's called a diffraction grating. It's a little window here, but it acts like a prism. It breaks the light into its different colors. So we're going to try to do this. Bring the camera, and I'm going to point my tube at the light, and as we look off to the side, we should be able to pick up a kind of a rainbow, and that is a continuous spectrum. So we're breaking that white light into all of its component colors. Okay, this time we're going to talk about emission spectra, and in talking about emission spectra, we're going to talk about fluorescent bulbs. I'm going to show you fluorescent bulbs, because fluorescent bulbs are different than incandescent bulbs. Incandescent bulbs, as I showed you, use a filament, a little piece of wire, and they run electricity through it, and that wire heats up to the point where it's glowing and it's producing visible light. Fluorescent bulbs also produce visible light, but they don't heat up a wire to produce it. What it does is it sets up an electric field in a tube, in a fluorescent tube that's full of gas, and that gas gets excited, just like we talked about, the fact that the electrons in those gas atoms get excited, and as they become de-excited, they give off photons, and we see those photons as the visible light. Let me show you the big difference when I take the camera here, and again, we're going to use our same diffraction grating, and we're going to point it at the fluorescent light, and you should notice that instead of an entire strip of all the different colors, you should just see several bright lines. So an emission spectrum is sometimes called a bright line spectrum. So it turns out that rather than producing all the colors that we combine to see as white light, like an incandescent bulb does, a fluorescent bulb actually just produces certain colors. There's a red, there's a green, there's a blue, etc., etc. And combining those individual frequencies, we see that overall as white light. Again, this is an emission spectrum because you see areas where there's no light, there's black, or certain frequencies are not produced. Only specific frequencies are produced by fluorescent bulbs. Okay, that tube that I was playing around with just a few slides ago was actually essentially a spectrometer. It's a diffraction grating and a small opening that allows light to enter the tube. And that's essentially what a spectrometer does. It takes light, allows it to pass into a tube via a slit, and then breaks it into its component colors. And so here I've got my spectrometer pointing in the direction of an incandescent light bulb. And as we've already talked about in Kirchhoff's first law, an incandescent light bulb is essentially a solid. The filament of the light bulb is a solid that is producing light. It's running electricity through it, and it's getting hot, and it gets so hot that it actually glows. It produces light. And it turns out it produces all the different colors of the spectrum. So when I'm pointing my spectrometer at this light bulb, white light is entering the spectrometer, and it's being broken into its component colors, which is this entire rainbow here. Again, that's Kirchhoff's first law. Now, let's now take my spectrometer and move it all the way over here. Notice what I'm doing. I'm pointing my spectrometer at the light bulb again. So again, I should be seeing the entire spectrum, but what do you notice? I'm seeing almost everything except for I'm seeing certain dark lines. Well, why is that? It's because the light that is leaving the light bulb and coming toward my spectrometer has to pass through a cloud of gas. And that cloud of gas is full of atoms of certain elements. And those atoms have electrons, and certain electrons are being excited. So that the photons, those particles of light that are leaving the light bulb, are passing through this gas on their way to my spectrometer. Some of them, however, are getting absorbed by the atoms of the gas. As they are absorbed, they excite the atoms in that gas into excited states. And so instead of all those photons reaching my spectrometer, they are being absorbed by the gas. And that's why I'm getting these dark lines. So notice that only certain frequencies are being absorbed. Well, why is that? Because those frequencies happen to have the proper energy to excite the atoms of this particular gas that's in the way. So that's what's called a dark line spectrum. So essentially it's an entire continuous spectrum minus a few certain frequencies. Now, remember I said that electrons, they get excited, then they de-excite in a hurry. So you might be wondering, well, gosh, why don't those electrons, they get excited, they de-excite, they emit a photon. Why don't those photons just fill in the gaps? Well, notice that the light coming from the light bulb, again, emits, gets absorbed by this gas. The gas will absorb and emit a photon of the same frequency. However, that electron, when it emits a photon, as it drops back down into its ground state, can emit it in any direction. So it doesn't necessarily emit it in the same direction as my spectrometer. And therefore, that's why it doesn't fill in the blank, or fill in that black spot. Now, that also helps to explain why, when I move my spectrometer over here, notice which direction my spectrometer is now pointing. It's pointing off into the darkness of space, right? It's not pointing toward the light bulb. It's pointing off, and it should be getting absolutely nothing showing up on its little reading here. And yet it does. Well, why is that? Because remember, these gas, now we're pointing it at the gas. The gas is still nearby a light source, or an energy source. So again, the light bulb is still exciting atoms in this gas. Those atoms are then de-exciting and emitting photons in all directions. Some of those photons are heading toward my spectrometer. And that's why I'm seeing what's called a bright line spectrum, or an emission spectrum. I should be seeing nothing, and yet I'm seeing certain frequencies. Well, why is that? Because the atoms in this gas have absorbed energy from this nearby star, or this nearby light bulb, and have emitted photons of those same energies, which I'm seeing now as a bright line spectrum. Okay, this slide is actually very similar to a diagram you'll find on page 111 of your book. And one thing I really want to point out, it's probably the most important thing in looking at this diagram, is I'll ask you, by looking at the spectrum view of this absorption spectrum. Now, first of all, you should notice this is an absorption spectrum. It looks like it's all the different colors, with the exception of a few frequencies are missing. Now, if you only had that spectrum of a star, could you tell the color of the star? And it turns out you wouldn't be able to. All this tells you, the only thing that an absorption spectrum of a star tells you, is essentially the composition of the star. Because notice it's missing certain dark lines. And those dark lines are characteristic of a particular element. In this case, it's hydrogen. So we know there's hydrogen in this star because hydrogen atoms in that star's atmosphere are essentially absorbing certain frequencies. And again, each element has its own kind of electron structure, electron energy level structure. So it's kind of like a fingerprint. So we know the composition of the star, but that's all we know. We don't know its color. We know that it produces blue light and purple light and green light and yellow light and orange light and red light. We don't know how those overall mix, what the mixture winds up being. Now, let's look at this other chart down here, because this is a more common representation. These days, instead of having a kind of a rainbow spectrum like that, you have what's called a light curve. It's an intensity versus wavelength kind of graph. Now, can I ask you what color the star is? You should be saying it's a bluish star, because notice that the intensity, it's producing all this light. This star is producing all the different colors, with the exception of here. Notice this little dip is your dark line, because notice that it's not very, that light at that particular wavelength is not very intense. But notice that this star is producing a lot more purple and blue than it is red. So overall, when you combine all these different relative light intensities, you're going to wind up with a star that is more bluish. But by just looking at the star's absorption spectrum, you can't tell its color. All you can tell is its composition. In order to find out its color, you have to look at the relative intensities of all those different types of light. And in order to do that, you need to have a light curve. Okay, just to reinforce what we know about the different types of spectra, I wanted to show you a little simulation. First of all, here's a continuous spectrum that shows all the visible wavelengths from 400 nanometers to 700 nanometers. And it's a continuous spectrum, so you would expect to see the entire rainbow. Now let's check out an emission spectrum. And I can choose now an element. Like I said, all elements have different numbers of protons and therefore different structures of electron orbits, and therefore essentially fingerprints. So let's choose hydrogen. That's what hydrogen's emission spectrum would look like compared to, let me click it off and let's put helium on there. Notice they're different, right? They've got a different fingerprint. I could choose, let's see, molecules, right? Or ionized helium. So that's one way that you learn about the composition of stuff in space, whether it's a cloud of gas and dust or a star. Now, if you're looking actually at a star, you're more likely to see an absorption spectrum than an emission spectrum. So let me pop on an absorption spectrum. And in this case, I do have to choose a spectral type. And we're going to look for hydrogen. So notice for a G2 star, which is actually like our sun. And again, the spectral type and the luminosity class, we're going to get to this in chapter 13. So that's a little bit kind of ahead of the game here. But notice that when I'm looking at an absorption spectrum for this particular star, I'm seeing almost all the colors, with the exception of I'm seeing some dark lines. And that's because this star has hydrogen in its atmosphere. So the star is actually producing at its core all the different colors. But by the time the light is getting to the atmosphere of the star, the elements, in this case hydrogen, in the atmosphere are absorbing certain photons, and therefore we're seeing these dark lines. So that's a dark line spectrum, also known as an absorption spectrum.
Okay, so I'm going to try to illustrate the Doppler effect by using this. It's actually a little bell, or notice that we have a certain frequency when the ball is stationary. But I'm going to swing the ball over my head, and you should hopefully notice a difference in the pitch as the ball comes toward you and as it goes away from you. So again, this is the at-rest frequency. Did you hear a difference? That's the Doppler effect. And one thing that's very important to understand about the Doppler effect is that the Doppler effect applies to anything, any waves. So that includes sound waves like you just heard, but it also would include any other type of wave, including light waves, not just visible light, but all the different frequencies in the electromagnetic spectrum.
Since most of you are familiar with the term Doppler in reference to weather, I would be remiss if I didn't share this little graphic with you. This is actually a graphic that I put together several years ago when I worked at USA Today, explaining Doppler radar. Now, before I even get into Doppler radar, let me first of all talk about radar, which is radar detection and ranging, radio detection and ranging. It was developed back in World War II, initially to detect enemy aircraft. So what essentially scientists did, or engineers did, was they sent out bursts of electromagnetic radiation, usually in the microwave frequencies, and send off a pulse and wait for it to hit something and then reflect back. And they would measure the amount of time that it took for that wave traveling at the speed of light to go out and return. And that was waved, and once you knew how long it took for the round trip and you knew the speed of light, you could determine the distance. So that was a way of ranging, and initially the intent was to, again, to look for enemy aircraft and that sort of thing. But what engineers quickly realized was that they weren't just picking up on aircraft, they were picking up on birds, and they were also picking up on precipitation, rain, hail, etc., etc. So it quickly went from having a military application only to having a weather application. Now you can actually see rain in the distance. Then, years later, it was realized that the frequency of the pulse that you sent out was different than the frequency of the pulse being received. There was a shift there, and that was because of the relative motion of the object that was being struck by the microwave pulse. So the pulse would get sent out at a certain frequency, hit a moving raindrop or a moving hailstone or whatever, and be reflected back, but with a slight shift in its frequency, a slight Doppler shift. And once you knew the amount of Doppler shift, you could figure out how fast that object was moving, the raindrop, the hailstone, that would give you an indication of the winds inside the storm. So this became huge. So not only were you able to tell how far away the precipitation was, you can actually tell the wind speeds within the thunderstorm, which becomes very useful in detecting whether or not there's rotation in a thunderstorm. Once you know the wind profile within the thunderstorm, you can see if there's rotation inside the thunderstorm, which could potentially lead to a tornado. So that's why Doppler radar is so very important when it comes to severe weather coverage. Okay, so here's a way of demonstrating the Doppler shift, and I'm going to go ahead and we have a source labeled S, and we have an observer. I'm going to kind of spread them apart a little bit here, and now the sources are obviously going to be emitting a wave. So notice my source has started to emit a wave, and that wave is now traveling to my observer. And we can see the wavelength of the wave that's received by the observer. We'll notice that in this case, when the source is stationary with respect to the observer, the wave detected by the observer is the same wavelength and therefore the same frequency. Now let me move my source, let me have my source move toward the observer, and actually it's going to then pass the observer and then move away from the observer. And notice what happens. When we consider the frequency of the wave received by the observer. Notice how the frequency goes up as the source approaches the observer, and then it decreases, then it becomes smaller as it goes away from the observer. Again, we saw both blue shifting as the source approached the observer, and then red shifting as the source moved away from the observer.